So the aim of this video is to couple a stack of 6 tapes, which is drawn here as a box, with the resistor in parallel, and to check the impact that the resistor has on the quenching of the superconducting stack. In another simulation, I already simulated such a stack without a coupled resistor, so all the current was flowing just into the stack. And now we want to see how the current distributes over the two paths, one through the stack and one through the resistor, over this transient time period of the quenching. So in this video I'll only show you the modifications made in order to couple that circuit, and I'll also show you how to create an extruded mesh with the GUI. But I won't show you all the setup processes that I already did for just the stack simulation, so you can have a look at the other video that was already uploaded to the YouTube channel to get into the stack itself. This video is focusing on the circuit coupling. So first I'm going to create a new project. I call it stack circuit coupling. And I'm going to build the stack geometry here. So the same as in the other video. Okay, so that's the geometry. We have the airbox, we have the stack in the middle, and we have a middle volume to keep track of the quench initiated there. And now I'll show you how to construct this extruded mesh. So we go to extrude, build all the previous elements, select the extrude mode such that we can also capture the airbox around, and then select all the layers that we want to have the extruded mesh in. So basically I could select all volumes and then deselect the airbox. And now it says I have 29 sublayers. It's because I'll have 29 layers in that direction, and I have to give the number of extrusion layers that I want to have per sublayer. So how many mesh layers I want to have. So it's going to be 6 for the copper. We start from the smallest Z coordinate and then in ascending order. So we're going to start here and then go up. So 6 for the copper, 6 for the substrate, 3 for the Repco layer, and then 6 for copper and 6 for the connection. And then we'll start over again with the same. Well, and I end up with 1 Repco layer and then the copper layer, so everything makes sense. I apply that and extrude it. Alright, so you can see it's extruded in that direction. That is the, such that we have this layered mesh in the end. We confirm the model changes and we go on to the material and the shared expression definition. That is mostly the same as in the stack video, so I'm just gonna do it and then later show you what is different. Okay, so now we have all the material definition, we have assigned the volumes to them, and have the two shared regions, conductor and fixed temperature, as same as in the other video. And now I'm going to add 2 expressions. One is the value of my resistor that I'll couple, so it's 1e minus 6, and the second one is the operating current. which is a ramp within 3 seconds up to 1.5 times the IC of the stack. Okay, now we can continue to the physics section. And here we're going to define our H5 physics as usual, and then the thermal coupling as well. So the thermal one will be in the conductor, phi will be in the air region. Okay, so that's the conducting region, H, and for phi I still need to make the air region visible. So yes, now it should be visible. Yes. So I can select the air region now. Then I'm gonna choose H5 coupling. I'm gonna choose Joule heating in the conducting region to couple it to the magnetic simulation. I set a gauge at 1 point, engage it to 0, and now I'm gonna supply that current or the circuit coupling. So my port is gonna be that entrance circulation loop around the stack. I'm gonna select it. Okay, that's the circulation loop, and now we have to select. Either we could just set our current as in the previous video, or now we're gonna put the circuit coupling here. So for this I can take lump V over R, which is the current flowing to my resistor, plus the current flowing through my stack, which is lump I. So that's the I flowing through that region that is enclosed by the circulation loop, and they should add up to the operational current. That's my circuit coupling equation that has to be fulfilled. Okay, so that's everything for the physics, and now we can define our simulation. So I'm gonna choose transient type with implicit Euler, 0 to 5 seconds with a time step of 50 milliseconds. Gonna run it on one node, and it's gonna take a bit longer than 3 hours, so let's say 200 minutes as timeout. Then we can create the mesh. With the max size 1e-3, and let's see where we end up with. And then as outputs we can, for example, take some discrete outputs. So one is the current flowing through the stack, which is lump I. And then as a second discrete output I can put the current through the resistor, which is lump V over R. Alright. Then I can make some few changes in the script. So first I need to scale my mesh in Z direction, because again I just build it 10 times bigger as it is to make it easier to select the volumes. Then I can reduce the order of phi and the order of t. Set an initial temperature value everywhere. To 77 Kelvin. I also need to set, or I forgot to set the constraint for for the heat solid. So I can do that also in the scripting interface and just add it here and constrain the define temperature fixed reasons to 77 Kelvin. Exactly. So what else? One thing, well, you can see now there's this lump interaction, and you can here see that to our formulation we added this circuit coupling formula. And what we can do now, as we also did in the other video but adapted for this new circuit coupling formulation, we can linearize our formulation for the Newton iterations. So instead of taking this on the whole conductor, we'll split it up, and we're gonna take this one for all the conducting regions which are non-superconducting. So the substrate copper and the connection. Right. And then for the superconducting region, we can take this linearized version. Exactly. That's it. We could maybe also print out the total number of degrees of freedom. Okay. And we can also print out for the first time steps the number the currents. But we don't need to print it out, we can just like to check in the first time steps, and even if we don't print it out, it's gonna be in the results summary in the end. So those are all the changes that I will do in the script. And let's have a look at our mesh now. Okay, so we can see that we have a tetrahedral unstructured mesh here, and that here we have the layers inside the repco, inside the whole stack, all layers of the stack, and it extrudes towards the outside of the airbox. Okay, so now we can start running the simulation. Okay, we can take a look at the results now. So on the left hand side you can see our stack, and then it shows the temperature, and it's gonna be as before, rising from the middle towards the outside, but you can already see from the scale that it's not heating up as hot as it was without the coupled quench protection resistor, which is a good sign because that's actually what the resistor should do. It should, when the current exceeds the critical current in the stack, it should take over some current and therefore prevent the quench or prevent the temperature rise to be too sudden and too high. And on the right hand side you can see the current distribution over the stacks, and then also the resistor in blue at the right hand side. So in the beginning we have very low voltage, we have a very low current running through the resistor in comparison to the currents running in the tapes of the stack. We can see that we have higher currents on the outer layers, Repco layers in the stack, and then it redistributes towards the middle. So I can play now this video, and you can see that the outer layers are rising and then it distributes towards the middle, and then we can see a sudden rise in the voltage and also sudden rise in the current flowing through the resistor, and we can see a heating up starting from the middle towards the outside of the tape. So I can run it again. So now it reaches the critical current and we have a sudden rise in the current of the resistor and also in the voltage. If we compare that now to the results that we had before, so on top you can see the results of the stack, same setup without a coupled resistor, and at the bottom you'll see it with the resistor coupled, so with this resistor current here, and we can see the difference in the currents as well as in the temperature rise on the right hand side. So in the beginning it's very similar, and then at some point when it reaches the critical current the resistor takes much more current and therefore there's less current in the copper layers, and the temperature rise is also lower, much lower than in the case without the quench protection resistor. So that's the expected result, and the simulation shows that this holds, and we can couple whatever lumped circuits that we want to our finite element simulation of the stack.